13 billion years ago, something impossible happened. The universe was barely 500 million years old. It was still emerging from a period of total darkness. Galaxies the size of our Milky Way suddenly blazed into existence. James Webb just found 300 of them. They glow a deep blood red in the infrared light. They contain billions of stars that should not exist yet. According to every model we have, there was not enough time. Dark matter had not yet gathered into massive halos. A thick hydrogen fog should have choked their brilliant light. These impossible galaxies break the laws of cosmic evolution. Picture a newborn infant learning to speak full sentences. Imagine this happening within just minutes of its birth. That is essentially what James Webb just witnessed. It saw this happen in the infant universe. Researchers at the University of Missouri scanned 4 patches of space. They found 300 objects glowing far brighter than they should. They were brighter than anything should be at that immense distance. These were not just ordinary distant galaxies. They were true cosmic impossibilities. Here is the fundamental problem they present to us. When you look deep into space, you are seeing the past. Light takes a very long time to travel across the cosmos. The farther away an object is, the older the light is. These newly discovered objects sit incredibly far away. We are viewing them as they appeared long ago, 500 to 700 million years after the Big Bang. The universe itself is only 13.8 billion years old. That means we are watching events from when everything was new. According to our current understanding of physics, galaxies need time. They need a great deal of time to grow and mature. Stars must form from collapsing clouds of hydrogen and helium. Gravity needs to pull all of that matter together slowly. This process happens over many millions of years. Dark matter halos have to assemble first. They create the invisible scaffolding that holds matter in place. This entire process follows very specific physical rules. The rules dictate how fast things can possibly happen, but these 300 objects ignored those rules completely. They shine with the brightness of mature galaxies. They are packed with many billions of individual stars. Some contain nearly as much stellar mass as our own Milky Way. That is like finding a fully grown oak tree, an oak tree sprouting from soil that was tilled only yesterday. The timeline for this simply does not work. Hao Jingyan is the astronomy professor leading this research. He calls them candidate galaxies for now. Scientists need much more data to confirm what they are. Right now, they appear as tiny red dots in Webb's images, but their spectral signatures suggest they are massive stellar cities, cities that assembled themselves at an impossible speed. The discovery challenges something called the ΛCDM model. This is our best framework for understanding the cosmos. It explains how the cosmos evolved from a smooth, hot soup, a soup of particles, into the structured universe we see today. The model predicts that small structures must form first. They then gradually merge into much larger ones over time. Dwarf galaxies should always come before the giant galaxies. Baby stars should come before mature stellar populations. These 300 objects flip that script entirely. They suggest the early universe was far more dynamic. It was more violent than we had ever imagined. Matter might have clumped together through unknown processes that we have not yet discovered or theorized. Or perhaps our fundamental assumptions need serious revision. Over 80% of these mysterious objects fall into a category. Astronomers call this category extremely red objects. Their light is strikingly brighter in certain infrared wavelengths. This redness tells us something crucial about their age. It also tells us about their incredible distance, but it also deepens the mystery of how they formed so fast. Something in the infant cosmos was accelerating galaxy formation. It pushed it beyond anything our current physics allows. The question keeping astronomers awake at night is simple. What force could possibly work that quickly? Before these impossible galaxies could even form, the universe was dark. It spent hundreds of millions of years in complete darkness. This was not the simple darkness of a moonless night. This was an absolute and total cosmic blackness. No stars existed yet anywhere in the universe. No galaxies glowed with the light of stellar populations. The entire universe was a cold and lightless void. The cosmic dark ages began 380,000 years after the Big Bang. At that precise moment, the universe had finally cooled enough. It cooled enough for electrons to bond with hydrogen nuclei. This process created the very first neutral atoms. This critical event is called recombination. Before recombination, the universe was an opaque plasma. Photons constantly scattered off of free-roaming electrons. Light could not travel more than a few feet without hitting something. When neutral hydrogen formed, photons suddenly had room to move. The universe became transparent for the very first time. But here is the cosmic twist in the story. There was nothing creating any new light at that time. The leftover energy from the Big Bang was still racing outward, but it was fading fast as space itself continued to expand. Within a few million years, the cosmos went completely dark. Imagine floating in this vast primordial void. In every direction you look, you see only blackness. No stars are twinkling and no nebulas are glowing. The only thing filling space is a thin fog of gas, a fog of neutral hydrogen gas, invisible in the dark. This gas absorbed any ultraviolet light that might have existed. This made the profound darkness even more complete. A single photon trying to escape would be trapped. It would be absorbed by hydrogen atoms before traveling far. Dark matter was there in the darkness, though. We cannot see dark matter because it does not interact with light, but its immense gravity was already hard at work. It was pulling the hydrogen gas into invisible filaments. These dark matter halos were slowly building the foundation. They were building the foundation for all future galaxies. But without stars, without any source of light at all, this cosmic construction happened in total silence and darkness. The Dark Ages lasted for a very long time, somewhere between 400 million and 600 million years. Scientists debate the exact timeline of this period. We cannot observe this era of cosmic history directly. The light from that time never actually reaches us. The thick hydrogen fog trapped all of it long ago. What we do know comes from powerful computer simulations. It also comes from studying what came immediately after. During these dark centuries, the universe's temperature dropped. It dropped to a temperature that was nearly absolute zero. The hydrogen gas drifting through space became incredibly cold. It reached temperatures around minus 450 degrees Fahrenheit. Everything was cold, completely dark and utterly still. The entire universe was waiting for something to happen. But beneath this apparent calm, gravity kept working. Dense regions of dark matter grew even denser. Hydrogen gas fell into these deep gravitational wells. It piled up over time, getting compressed by gravity. Immense pressure began to build in these dense gas clouds. And when pressure and density reach critical thresholds, something absolutely spectacular and transformative happens. The very first stars in the universe finally ignited. These primordial suns were made entirely of hydrogen and helium. They burned incredibly hot and incredibly bright. They were probably 100 times more massive than our own Sunday. They lived very fast lives, and they died very violently. They exploded as supernovas within just a few million years, but their brilliant light had already changed everything. Those very first stars ended the cosmic dark ages, and somehow within just a few 100 million years of that first light, 300 massive galaxies were already shining brightly. The timeline for this feels impossibly tight. James Webb does not just take pictures of distant space. It functions as a powerful time machine for astronomers. It captures light that has been traveling toward us for billions of years. Understanding how this works reveals why these galaxies are so shocking. Light moves incredibly fast, through the vacuum of space. In one single second, it travels 186,000 miles. That speed sounds almost instantaneous to us, until you start to consider the vast cosmic distances. The nearest star beyond our own sun is over 4 light-years away. This means its light takes 4 years to finally reach us. When we see that star in the night sky, we are actually seeing what it looked like 4 years ago. Now let's scale that concept up to galactic distances. The 300 mysterious objects Webb discovered are far away. They sit roughly 13 billion light-years away from us. Their light has been racing through space for 13 billion years. When we see them with our telescopes now, we are watching events that happened when the universe was very young, when it was only 500 to 700 million years old. We are literally looking backward through cosmic time. But there is a complication that makes this even stranger. The universe itself is not static, it is dynamic. Space itself is constantly expanding, stretching like dough. As space expands, the light traveling through it gets stretched too. This stretching shifts the light's wavelength toward the red end of the spectrum. This phenomenon is known as cosmological redshift. Think about the sound of an ambulance siren. When it drives toward you, the sound waves compress. This makes the pitch of the siren rise. When it drives away from you, the waves stretch out. This makes the pitch of the siren drop. Light works in a very similar kind of way. Objects that are moving away from us have their light stretched. Their light is stretched to longer and redder wavelengths. The faster they are receding from us, the more their light redshifts. For extremely distant galaxies, this redshift is dramatic. Light that left them as ultraviolet or visible blue light gets stretched. It gets stretched so much it becomes infrared light by the time it reaches Earth. This is why the Hubble Space Telescope missed these objects. Hubble primarily sees visible and ultraviolet light. Many of these early galaxies had redshifted beyond Hubble's range. James Webb was specifically built to see this infrared light. Its 18 hexagonal mirrors collect this invisible radiation. Its instruments can detect wavelengths from 6 to 28 micrometers. That specific range is perfect for finding the most distant galaxies. Their light has been stretched by cosmic expansion. The telescope measures how much a galaxy's light has redshifted. This measurement tells astronomers the galaxy's distance. It therefore tells them how long ago we are seeing it. A galaxy with a redshift value of 10 is very old. It existed roughly 13.2 billion years ago. A higher redshift means more distant and more ancient. Webb's near-infrared camera captured the 300 mysterious objects. It did this during its deep field surveys of the sky. These surveys stare at tiny patches of apparently empty sky. They stare for hours, collecting every single photon possible. What looks completely empty to our eyes explodes with distant galaxies. It explodes with them in Webb's powerful infrared view. Each of those 300 red dots represents a distant galaxy, a galaxy so far away that its light has been traveling for eons, traveling since before the Earth even existed, traveling since before our own sun had formed, traveling since before most stars in our galaxy were born. We are witnessing the cosmic dawn itself with our own eyes. But here is what troubles the scientists so much. These galaxies should not be visible at all yet. Finding the oldest galaxies in the universe requires clever detective work. Astronomers cannot just look for the faintest objects. They need a specific method that identifies these galaxies, a method that filters out everything else in the image. That is where the clever dropout technique comes in. The method exploits a specific property of hydrogen gas. Hydrogen atoms absorb ultraviolet light at a specific wavelength. This wavelength is known as the Lyman limit. This absorption happens at 91.2 nanometers. Ultraviolet light from a distant galaxy passes through clouds of hydrogen. All wavelengths shorter than the Lyman limit get absorbed. The galaxy essentially drops out of view at those wavelengths. Here is how astronomers use this powerful effect. They photograph the same region of space with multiple filters. Each filter captures a different color or wavelength of light. A galaxy might appear bright in the redder filters, but it might completely disappear in the bluer ones. This vanishing act signals that we are seeing a distant galaxy, so distant that its Lyman break has redshifted into the near-infrared. Bangjian Sun and Jing Yang used this technique on the James Webb data. They examined over 500 square arc-minutes of the sky. They were specifically looking for objects with a certain pattern, objects that appeared in longer wavelength filters but dropped out in shorter ones. The dropout pattern acts like a unique cosmic fingerprint. It is a fingerprint that identifies the earliest galaxies. The technique works because of the expansion of the universe. The farther away a galaxy sits, the more its light stretches. For a galaxy at a redshift of 7, its Lyman break is shifted. It has shifted far into the near-infrared part of the spectrum. For even more distant galaxies, the break shifts even further. By carefully comparing images taken through different filters, astronomers can estimate how far the Lyman break has moved. This tells them how distant the galaxy is from us. This method is not completely foolproof, however. Other types of objects can sometimes mimic the dropout pattern. A dusty nearby galaxy might look very red. It might fail to appear in the blue filters. A quasar or an active black hole could produce similar colors. That is why astronomers call these findings candidate galaxies. They are not yet confirmed discoveries of early galaxies. Additional observations are needed to rule out any imposters. The researchers found 300 candidates in this way. Each one of them showed the telltale dropout signature. They appeared bright in some infrared wavelengths but vanished in others. The pattern suggested these objects sat at incredibly high redshifts. This means they existed very early in cosmic history. But something about the discovery was very wrong. The number of dropout candidates was much higher than expected. Previous surveys and theoretical models had predicted fewer. They predicted fewer massive galaxies in the early universe. Finding 300 bright ones in a relatively small area of sky was a shock. It suggested the infant cosmos was more crowded than anyone thought. Even more puzzling was their incredible brightness. These were not faint smudges, barely visible at the detection limits. Many of them glowed very powerfully in the infrared. That high luminosity implied they contained enormous numbers of stars. Perhaps they contained many billions of individual stars. How did so many stars form so incredibly quickly? The dropout technique had revealed something completely unexpected. The early universe apparently filled with large galaxies. It filled with them much faster than our physics should allow. When you look at the images of the 300 mysterious objects, one single feature completely dominates the view. They are all red, not pink, not orange, but a deep dark red. This specific coloration is not just decorative, it is a critical clue about their age and their nature. Over 80% of the dropout candidates fall into a special category. They are called extremely red objects, or EROs. The technical definition for this category is straightforward. Their brightness in one infrared filter exceeds their brightness in another. It exceeds it by more than 2 full magnitudes. In practical terms, they are about 6 times brighter at longer wavelengths. They are 6 times brighter compared to shorter infrared wavelengths. That is an enormous and very significant color difference. Why does this extreme redness matter so much to astronomers? In astronomy, the color of an object reveals its history. When stars first form, they burn very hot and blue. Young massive stars emit most of their energy as ultraviolet and blue light. As stars begin to age, they cool down and they redden. Old stellar populations are dominated by red giant stars. These populations produce more red and infrared light. Red galaxies typically contain older, more mature stars. But these 300 galaxies are not red because they are old. They existed when the universe was incredibly young. Their deep redness comes from redshift combined with possible dust. Cosmic expansion stretches their light across billions of years. Wavelengths that started as visible blue light get pushed. They get pushed far into the infrared part of the spectrum. Ultraviolet light becomes visible red light to us. Visible red light becomes near-infrared light. The more distant a galaxy is, the more extreme this effect becomes. For objects at redshifts around 7 to 10, the effect is huge. Light that was emitted in the ultraviolet ends up being observed as mid-infrared. This is why Webb's mid-infrared instrument found additional detail. It found this detail in 137 of the candidates. These galaxies were so distant, their light had stretched completely. It had stretched into the mid-infrared range of the spectrum. Cosmic dust also plays a very important role in this. If these young galaxies already contain significant amounts of dust, that dust would absorb the blue and ultraviolet light. It would allow the red light to pass through relatively unimpeded. This would make them appear to be even redder. But here is the problem with that particular explanation. Where would all of that cosmic dust come from? So early dust grains in space are made of heavy elements. Elements like carbon, silicon, and iron. These elements do not exist naturally in the universe. They only form deep inside of stars through nuclear fusion. When massive stars explode as supernovas, they scatter these elements. They scatter them into space where they can condense into dust. But this entire process takes a great deal of time. Multiple generations of stars need to live and die. They must do this before significant dust can accumulate. For these galaxies to be dusty at such an early epoch, it implies incredibly rapid and efficient stellar evolution. Stars had to form live their entire lifetimes and explode. They had to create dust all within the first few 100 million years. That is possible, but it requires extreme star formation rates. Rates far exceeding anything we observe in modern galaxies. The redness also helps astronomers to estimate the distances. They measure exactly which wavelengths each galaxy appears in, and they measure which wavelengths it drops out from. This allows them to calculate its redshift value. This gives an approximate distance and age for the object. For the 300 candidates, the calculations were surprising. 2/3 of them sit at redshifts between 1 and 4. This means they are closer and younger than initially thought, but 1/3 of them potentially sit at much higher redshifts. Redshifts above 7 or even as high as 10, those are the truly problematic ones for our theories. If they are confirmed, they represent massive, impossible galaxies. The blood-red glow is not just aesthetically striking, it is hard evidence of cosmic processes happening faster than our current models of physics predict. Building a galaxy from scratch takes a lot of time, or at least that is what it should do according to our models. The 300 objects Webb discovered seem to have skipped several steps. They skipped steps in the Cosmic Construction Manual. Understanding why this is a problem requires looking at how stars form. Star formation begins inside of giant molecular clouds. These are vast regions of cold gas and dust floating in space. These clouds are mostly hydrogen with traces of helium. Gravity slowly pulls the gas inward, creating denser clumps. As a single clump collapses, it heats up significantly. When its core reaches about 18 million degrees Fahrenheit, nuclear fusion finally ignites, and a new star is born. This process has certain physical limits, however. You cannot just cram infinite amounts of gas into stars instantly. Physics imposes very specific speed limits on star formation. The main bottleneck in this process is called feedback. When massive stars form, they produce intense radiation. They also produce powerful stellar winds of particles. This energy blasts the surrounding gas away from the star. This makes it much harder for new stars to form nearby. When massive stars die as supernovas, the explosions are huge. They scatter even more of the gas in the region. These feedback mechanisms act like cosmic pressure relief valves. They prevent the gas clouds from collapsing too quickly. Without feedback, all the gas in a galaxy might turn into stars. It could do so within just a few million years. With feedback, the process stretches out over billions of years. Modern galaxies convert their gas into stars at modest rates. The Milky Way produces about 3 new solar masses of stars per year. Some active galaxies manage 10 to 20 solar masses annually. A few extreme starburst galaxies can hit 100 solar masses per year. But these are very rare, and they are very short-lived. Now consider what the 300 mysterious objects accomplished. If they truly contain stellar masses comparable to our Milky Way, that means billions of solar masses worth of stars. Our own galaxy has roughly 100 billion stars in total. These early galaxies appear to have assembled similar numbers. They did this within just a few 100 million years. You can do the math to see the problem. To build 100 billion solar masses of stars in 500 million years, it requires an average star formation rate of 200 solar masses per year. This rate must be sustained for 500 million years straight. That is 10 to 20 times faster than the most extreme starburst galaxies today. And remember, this high rate needs to be sustained. Most starburst galaxies burn out very quickly. The feedback from all of their massive young stars blows away the remaining gas. This shuts down any further star formation in the galaxy. These early galaxies somehow managed to avoid that fate, or they overcame it through processes that we do not yet understand. One possibility is that star formation worked differently back then. The gas in the early universe was much denser. It had not yet been enriched with any heavy elements. Perhaps this primordial gas collapsed more efficiently than modern gas. Maybe the first stars formed in massive clusters rather than individually. This could allow for much higher star formation rates. Another theory suggests these galaxies experienced multiple intense bursts. Rather than steady gradual growth, they might have had violent episodes. Star formation rates could have temporarily skyrocketed to extreme levels, perhaps 1,000 solar masses per year, or even more. A few brief bursts like that could account for their large populations, but both of these explanations require very special conditions. They require conditions or mechanisms that our current models do not include. Standard galaxy formation theory assumes gradual feedback-regulated growth. These 300 objects are telling a very different story. They formed stars much faster than the universe should have allowed, and that is making astronomers question everything they thought they knew. Every galaxy that we observe today sits inside a massive halo, a halo of a mysterious substance called dark matter. This invisible substance does not emit any form of light. It does not interact with ordinary matter except through gravity. But its powerful gravitational pull is what holds galaxies together. It is what shapes their formation over cosmic time. The problem is that 500 million years after the Big Bang, these massive dark matter structures should not have existed yet. Dark matter makes up about 84% of all matter. It formed shortly after the Big Bang, likely from exotic particles. Immediately after the Big Bang, dark matter was spread out evenly. There were only tiny density variations from place to place. Over time, gravity amplified these small initial differences. Think of it like cream that has been stirred into coffee. At first, the cream is almost evenly distributed throughout the liquid, but if you let it sit for a while, tiny currents cause it to clump. Dark matter clumps in the very same way, but much more slowly. The densest regions pull in more dark matter from their surroundings. They grow larger and denser over many millions of years. These growing clumps of dark matter create deep gravitational wells. Ordinary hydrogen and helium gas falls into these wells. It gathers in the centers of these dark matter halos. As the gas becomes dense enough, stars can finally begin to form. The The dark matter halo acts like a kind of cosmic scaffolding. It provides the gravitational structure that holds the galaxy together. This process follows what is known as a hierarchical timeline. Small dark matter clumps form first, creating dwarf galaxies. These dwarf galaxies then merge over billions of years. They build progressively larger and larger galaxies. By the time the universe reaches its current age of 13.8 billion years, massive dark matter halos have had time to assemble. They can support giant galaxies like our own Milky Way. But this hierarchical assembly process takes a very long time. Cosmological simulations show that truly massive dark matter halos should not exist. They should not exist until at least a few billion years after the Big Bang. At 500 million years, only the smaller halos should have formed. Yet the 300 mysterious objects appear to be large, mature galaxies. If this is confirmed, they must be sitting inside massive dark matter halos. Halos that simply should not have had enough time to grow that large. This creates a very serious problem for our understanding of structure formation. Claudia Lagos is a cosmology researcher who is studying these early galaxies. She put the problem quite bluntly in a recent interview. Having extremely massive galaxies so early in cosmic history is a challenge. It poses significant challenges to our standard model of cosmology. The ΛCDM framework predicts specific growth rates for dark matter structures. These newly discovered galaxies seem to exceed those predictions. Several different explanations have been proposed to solve this problem. Maybe dark matter clumped together faster in certain rare regions. Perhaps some exotic physics during the earliest moments created large structures. Or possibly dark matter is not purely cold, as we assume. It could contain a component that behaves differently than we expected. Another possibility is much more radical in its implications. What if these strange objects are not actually galaxies at all? Some astronomers have suggested they could be massive black holes. These black holes would be surrounded by accretion disks that mimic galaxies. Black holes are known to be able to form faster than dark matter halos. A sufficiently massive black hole feeding on surrounding gas could be very bright. It could produce the luminosity we are seeing without a full dark matter halo. But even that explanation has its own set of problems. How do such massive black holes form so incredibly quickly? The standard path to supermassive black holes requires millions of years of growth. These objects would need to bypass several stages of black hole evolution. The invisible scaffolding that should support these galaxies was not ready. Either the scaffolding formed much faster than our physics predicts, or these objects do not need scaffolding in the way that we think they do. Our home galaxy, the Milky Way, is an ancient cosmic city. It contains roughly 200 billion individual stars. It measures about 100,000 light-years across. It has been forming stars for over 13 billion years. The galaxy that we live in represents the culmination of eons of cosmic evolution. Now imagine finding something very similar to it. Imagine finding it when the universe was barely out of diapers. The story of the Milky Way began soon after the cosmic dark ages ended. Small proto-galaxies formed first in the early universe. Each of them contained perhaps a few million stars. Over billions of years, these smaller systems collided and merged. Each merger added more stars and gas to the growing galaxy. It gradually built the massive spiral structure that we see today. The process was very slow and very steady over time. Our galaxy's stellar disk took several billion years to settle. It took that long to settle into its current flat shape. The beautiful spiral arms formed relatively recently in cosmic terms. They probably formed within the last few billion years. The central bulge is packed with older, redder stars. It represents some of the earliest stellar populations in the galaxy. Even that ancient core took a great deal of time to assemble. Current estimates suggest the Milky Way gained most of its mass long ago. It happened between 8 and 10 billion years ago. Star formation in our galaxy peaked during that era. Then it gradually declined to the modest rate that we observe today. The galaxy's growth was very methodical and followed the timelines that are predicted by our cosmological models. Now let us look again at the 300 early galaxies. Some of them appear to contain stellar masses approaching the Milky Ways. Some of them may even match our galaxy's total stellar mass. That represents 10 to 100 billion solar masses of stars. But they achieved this incredible size in only a few 100 million years. They accomplished in a fraction of a billion years what took our galaxy over 10 billion. The comparison reveals just how abnormal these objects truly are. Imagine if a human infant grew from a newborn to a full adult size in 1 week. That is roughly the proportional time difference we are talking about. These galaxies must have undergone a compressed evolution at impossible speed. Their structure also differs from that of modern galaxies. Many of the early galaxies that have been observed by Webb show flattened disk shapes, or they show irregular tube-like structures in their morphology. They lack the organized spiral arms or elliptical symmetry that is common in the mature galaxies that we see today. They look chaotic, more like cosmic construction zones than finished cities. The Milky Way has benefited from over 13 billion years of chemical enrichment. Each generation of stars has added heavier elements to the gas supply. This has made the subsequent stellar populations more complex. Our own Sun, for example, is a third-generation star. It contains many elements that were forged in earlier stars. This enrichment process happens very gradually over cosmic time. These early galaxies had minimal chemical enrichment to work with. They formed from gas that was nearly pure hydrogen and helium, yet somehow they managed to build galaxy-scale stellar populations. They built them from this pristine primordial gas. The efficiency required for this exceeds anything we observe. It exceeds anything we observe in the modern universe. Think about all of the resources that would be involved in this. Our own galaxy consumed vast amounts of gas over billions of years. It did this to build up its current stellar population. It also lost enormous amounts of gas to stellar winds and supernovas. The net efficiency of star formation is relatively low. Much of the available gas never actually became stars. For the 300 early objects to reach comparable sizes so quickly, they must have converted their gas to stars with incredible efficiency. Either they were able to retain their gas much better, avoiding losses to feedback mechanisms that plague modern galaxies, or they somehow managed to funnel gas inward much faster than normal. Comparing them to the Milky Way highlights their impossible nature. They are like cosmic time travelers from the future. They are exhibiting mature characteristics before they had time to develop them. Let us put the timeline problem in a human perspective. The entire universe is 13.8 billion years old. Our planet Earth formed about 4.5 billion years ago. Complex life on Earth emerged roughly 600 million years ago. Modern humans appeared on the scene around 300,000 years ago. 500 million years sounds like an eternity to us, but in cosmic terms, it is barely a moment in time. 500 million years after the Big Bang, the universe was young. It was only 3.6% of its current age. To understand how young that is, imagine Earth's history. Imagine its entire 4.5 billion year history compressed into 1 year. 500 million years would be equivalent to just 40 days. We are talking about the cosmic equivalent of January here. During those first 500 million years, a lot had to happen. The cosmic dark ages had to come to an end. The very first stars in the universe had to form. Those stars had to live out their entire lives and then explode. Their debris had to enrich the surrounding gas with heavy elements. Second and third generation stars had to form from that enriched material. Gas clouds had to collapse and merge together. Star clusters had to become gravitationally bound together. All of this had to happen within what amounts to cosmic infancy. Current models suggest the first stars ignited around 100 million years. They ignited 100 million years after the Big Bang. These primordial suns were massive, burning hot and bright, but they died within just a few million years of their birth. Their powerful explosions seeded space with the first heavy elements. Second-generation stars began to form around 200 million years. The earliest confirmed galaxies before Webb's discoveries were found. They existed around 380 million years after the Big Bang. These were small systems, containing perhaps 10 to 100 million stars. They represented the expected early stage of galaxy formation. They were the small building blocks that would later merge. But the 300 mysterious objects appear to exist later, between 500 and 700 million years after the Big Bang. That is only 200 to 400 million years after the first stars formed. In that brief window of time, they somehow assembled huge stellar populations that are comparable to our modern Milky Way galaxy. Consider what this very short timeline requires. Stars themselves need a certain amount of time to form. A typical star-forming region in our galaxy produces stars over millions of years, but you need multiple star-forming regions operating at the same time. You need them to be operating simultaneously to build billions of stars. You need gas clouds to collapse, fragment, and ignite in coordinated waves. This must happen across the entire extent of the galaxy. Then there is the merger timeline to consider as well. If these large galaxies formed through the mergers of smaller proto-galaxies, those smaller systems had to exist first in order to merge. Each of those dwarf galaxies needs tens of millions of years to assemble. Then the mergers themselves take a great deal of time, typically 100 to 500 million years. This depends on the masses and velocities of the merging galaxies. Cramming all of these processes into just 500 million years is hard. It feels like trying to write an entire novel in just 1 hour. You might be able to produce something in that time, but it will not be polished or comprehensive in any way. Yet these early galaxies do not look like rough drafts. They contain massive stellar populations, suggesting mature systems. Joel Leha, an astrophysicist who is studying these objects, described them. He described them as being completely bananas. His team had expected to find small blue baby galaxies. They expected to find them in the early universe. Instead, they found red mature systems that had apparently jumped ahead. They had jumped ahead several developmental stages in their evolution. The timeline crisis is not just about the speed of formation. It is about the fundamental physical limits that are involved. Certain physical processes require a minimum amount of time. You cannot rush the process of nuclear fusion in a star. You cannot rush gravitational collapse beyond certain points. These galaxies seem to have done exactly that. Either our timeline of the early universe is wrong, or these objects followed a formation pathway we have not discovered. Out of the 300 dropout candidates that were found, over 240 of them fall into the extremely red object category. This is not just a minor detail in the story. It is a major clue that something very unusual happened in these systems. The extreme redness of these objects suggests processes beyond normal evolution. The technical definition uses what are known as magnitude differences. Magnitudes measure brightness on a logarithmic scale. Each step on the scale represents about 2.5 times more light. An extremely red object shows more than a 2 magnitude difference. It shows this between 2 specific infrared filters. That translates to being over 6 times brighter at longer wavelengths. It is 6 times brighter compared to shorter infrared wavelengths. Why does this level of extreme redness matter so much? Normal galaxies show color gradients, but not this extreme. Even old red galaxies in the nearby universe do not approach this level. They do not have this level of red excess in their light. The extremely red objects are so red that they stand out. They stand out as significant statistical outliers in the data. Several different factors could be contributing to their appearance. The most obvious one is, of course, cosmological redshift. As we discussed, the expansion of space stretches light to longer wavelengths. The farther away an object is, the more its light will shift toward the red. For galaxies at very high redshift, this effect is dramatic. But redshift alone does not fully explain their extreme nature. Theoretical models that include redshift predict certain color ranges. They predict these ranges for the early galaxies. Many of these 300 objects exceed those predictions. They are much redder than they should be, even for their distance. Cosmic dust is the next logical suspect in this case. Interstellar dust is known to preferentially absorb blue light. It allows the red light to pass through more easily. This is the same reason why our sunsets appear to be red. Dust particles in the atmosphere scatter the shorter blue wavelengths. The longer red wavelengths travel relatively unimpeded to our eyes. If these early galaxies contain substantial amounts of dust, it would certainly make them appear to be much redder. But as we mentioned earlier, the dust requires heavy elements, and those elements come from stellar evolution and supernovas, building up significant amounts of dust in the first few 100 million years. This requires exceptionally rapid and efficient stellar cycling. Stars must form, age, and die quickly enough to produce the dust. One possibility is that the first stars were extremely massive. They lived very short lives and produced disproportionate amounts of heavy elements. If enough of these primordial supergiants exploded early, they could have enriched the local environment with dust-forming elements. They could have done this within 100 million years or less. Another factor is the age of the stellar population. When a burst of star formation occurs, the galaxy initially glows blue. This is due to the massive young hot stars that have just formed. As those stars age and die, the remaining population shifts. It shifts towards smaller, longer-lived red stars. After a few 100 million years without any new star formation, a galaxy can become quite red in its appearance. This scenario implies the extremely red objects had intense star formation bursts. These bursts were then followed by a period of quiescence. They built up their stellar populations very quickly. Then for some reason they stopped forming any new stars. This would make them appear red without requiring extreme amounts of dust. Some astronomers have nicknamed these objects sleeping beauty galaxies. They are systems that formed very early and then went dormant. The challenge is explaining why they would stop forming stars. Modern galaxies stop forming stars when they run out of gas, or when feedback from stars and black holes heats or expels the gas. But these early galaxies existed in a universe still filled with pristine hydrogen. Gas was incredibly abundant everywhere in the early cosmos. What could have possibly shut them down so early? The mid-infrared instrument on Webb provides additional insight. It provides this for 137 of the extremely red objects. These observations can penetrate dust better than the near-infrared. This allows astronomers to see what is happening deep inside these systems. The data from this instrument confirms that many of them are distant. They are legitimately distant and incredibly bright. The extreme redness is not just a measurement quirk. It represents real physical properties that challenge our understanding. Determining an object's distance and age in astronomy is not easy. It requires more than just taking a simple picture of the object. Astronomers need to analyze how bright the object appears. They must do this at many different wavelengths of light. This rainbow of brightness measurements is called a spectral energy distribution. It is like a unique fingerprint that can reveal hidden properties. Here is how this particular scientific process works. Different types of cosmic objects emit light in characteristic patterns. Hot young stars pump out enormous amounts of ultraviolet and blue light. Cool old stars produce mainly red and infrared light. Gas clouds that are heated by star formation emit at specific wavelengths. Dust absorbs the short wavelengths and re-radiates them at longer wavelengths. By measuring the brightness across many different wavelengths, astronomers can determine what is producing the light. The research team measured the spectral energy distribution for each candidate. They used data from multiple different Webb instruments. These instruments cover different parts of the infrared spectrum. They also incorporated data from other telescopes when it was available. This helped them to build a comprehensive picture of each object's light. Then comes the very important analysis phase of the research. Astronomers compare the observed spectral energy distribution to theoretical models. These models predict what galaxies should look like. They predict what they should look like at different distances and with different properties. By finding the model that best matches the observations, researchers can estimate the galaxy's redshift stellar mass and age. The SED fitting for the 300 objects revealed some surprising results. About 2/3 of them appeared to be closer than initially thought. They were at redshifts between 1 and 4. That places them around 2 to 12 billion years in the past. This is still ancient by human standards, but not impossibly early. These closer objects are interesting, but they do not challenge cosmology. The remaining 1/3 of the objects, however, were different. They showed spectral energy distributions consistent with very high redshifts. Redshifts above 7, and some even reaching 10 or beyond. These objects, if the estimates are correct, are the problem. They existed less than 700 million years after the Big Bang. They are the ones that are causing all of the headaches for theorists. Their SEDs suggest that they have mature stellar populations. The light patterns match what you would expect from galaxies. Galaxies that contain billions of stars with a mix of different ages. Some of the stars in them appear to be several 100 million years old already. That is impossible if the galaxy formed just a few 100 million years after the Big Bang. It implies that star formation in these objects began even earlier. Perhaps it began within the first 200 million years. The stellar masses that were derived from the SED fitting also raise eyebrows. Several of the objects show masses between 10 and 100 billion solar masses. That is an enormous amount of stellar mass for such an early epoch. Building that much stellar mass requires converting vast amounts of gas. It requires converting it into stars at rates exceeding anything observed today. There is a great deal of uncertainty in these measurements, though. The process of SED fitting is not perfect by any means. The method relies on theoretical models that might not be complete. They might not fully capture the complexity of real galaxies. If these early systems evolved differently than modern galaxies, the models might be giving us incorrect results. The derived ages and masses of these objects could be overestimated. That is why astronomers are emphasizing that these are candidate galaxies. The spectral energy distribution analysis provides very strong evidence, but it is not definitive ironclad proof of their nature. The next step in the process is to use spectroscopy. This technique provides far more precise measurements. Spectroscopy spreads the light out into its component wavelengths. It reveals absorption and emission lines from specific elements. These lines have known rest wavelengths that we can measure in the lab. By measuring how much they have shifted in the galaxy's light, astronomers can determine the exact redshift with high precision. Spectroscopy can also reveal the chemical composition and temperature. It can reveal the density and other properties of the galaxy. Until spectroscopic observations confirm the distances and properties, some degree of uncertainty will remain about these objects. But the spectral energy distributions are already telling a compelling story. These objects, at least some of them, seem to be extraordinarily massive, and they seem to have formed extraordinarily early in the universe. They are pushing the boundaries of what the infant universe was capable of. What if the 300 mysterious objects are not actually galaxies at all? This is a question that is keeping some astronomers awake at night, because if they are something else entirely, it could solve the problem. It could explain their impossible properties without breaking physics. The leading alternative explanation is both fascinating and unsettling. They might be a theoretical object known as black hole stars. Black hole stars are theoretical objects that should not exist anymore. They are hypothesized to have formed in the very early universe. They would have formed under conditions that no longer occur today. Picture this scenario from the dawn of time. A massive star begins to collapse under its own gravity. Normally, it would either explode as a supernova or collapse. It would collapse into a neutron star or a black hole. But in the primordial universe with its unique conditions, something very different might have happened instead. The star's core would have collapsed into a black hole as expected, but instead of consuming the entire star, the black hole gets trapped. It gets trapped inside of the star's outer layers. The black hole sits at the very center, feeding on infalling material. The outer layers of the star remain intact for a time. The energy released by matter falling into the black hole prevents further collapse. It effectively stabilizes the entire structure for a while. The result of this process is a bizarre hybrid object. It looks like a normal star from the outside, glowing brightly. But it is powered by a black hole at its core, not nuclear fusion. These black hole stars could have grown to be enormous, potentially thousands of times larger than normal stars. And they could have shone incredibly brightly in the early universe. They could have mimicked the appearance of entire galaxies. This theory gained attention when astronomers discovered strange objects. They found them in Webb images that do not behave like galaxies. They are compact, extremely luminous, and very red. Some of them have been nicknamed little red dots. Their properties do not match expectations for either galaxies or quasars. Black hole stars could potentially fit these observations. If the 300 candidates are actually black hole stars, it would solve several of the problems they present. Black holes can form much faster than entire galaxies can. They do not require the presence of extensive dark matter halos. They do not need hundreds of millions of years of gradual star formation. A single black hole star forming within just a few million years could be bright. It could produce the high luminosity that we are seeing. The extreme brightness of these objects also makes sense. Matter falling into a black hole converts mass to energy with incredible efficiency. This process is far more efficient than nuclear fusion. Even a relatively small black hole feeding rapidly could outshine billions of stars. If dozens or hundreds of these black hole stars existed in the same region, their combined light would appear like a very bright galaxy. But there are some significant issues with this interpretation. Black hole stars, if they ever existed, should have been unstable. Most theoretical models predict they would collapse completely, or they would explode within just a few million years. Finding hundreds of them all at the same time seems unlikely, unless they were forming continuously over longer periods of time. Also, the spectral energy distribution analysis suggests extended structures. It does not suggest that they are simple point sources of light. Galaxies have a definite size, with light coming from distributed stars. Black hole stars should appear to be much more compact. Some of the 300 objects show hints of spatial extent. This does not fit the point source model of a black hole star. Another problem is the chemistry of the objects. Galaxies should show the spectral signatures of stars, gas and dust. Black hole stars would show very different signatures. Signatures related to accretion and extreme energy processes. Preliminary observations favor the galaxy interpretation so far, but much more data is needed to be certain about this. Erica Nelson, one of the astronomers studying these objects, acknowledged the possibility. She noted that if these things turn out to be a different kind of weird object, like faint quasars or something else, that would be just as interesting. It would be just as interesting as finding impossible galaxies. The truth of the matter probably lies somewhere in the middle. Some of the 300 objects are likely to be genuine early galaxies. Others might be misidentified quasars or active galactic nuclei. A few of them could be black hole stars if those exotic objects actually existed. Separating one from another requires detailed spectroscopic observations, but the fact that astronomers are seriously considering such exotic alternatives, it shows just how unexpected these new discoveries really are. The early universe was shrouded in an opaque and dense fog. This was not water vapor or some kind of cosmic dust. It was neutral hydrogen gas that was filling all of space. It was absorbing and scattering any light that tried to pass through it. Any galaxy trying to shine through this thick fog faced an impossible barrier. Photons could not travel more than a very short distance. A hydrogen atom would absorb them before they got very far. Yet somehow, the light from these 300 objects reached us. It reached us from across 13 billion years of space. Understanding this barrier requires knowing what neutral hydrogen does to light. A hydrogen atom consists of just one proton and one electron. When the electron orbits close to the nucleus, the atom is in its ground state. If a photon with exactly the right energy hits this atom, the electron will absorb the photon and jump to a higher energy level. The photon is completely destroyed in this process. The key phrase here is exactly the right energy. Hydrogen atoms absorb ultraviolet light at very specific wavelengths. The most important of these absorption features happens at the Lyman alpha line. This is at about 121 nanometers. Even more critically, hydrogen absorbs all ultraviolet light shorter than 91 nanometers. This is the Lyman limit that we discussed earlier. In the early universe, space was filled with these neutral hydrogen atoms. Any ultraviolet photon traveling through this fog would be absorbed. It would be absorbed almost immediately after it was emitted. The average distance a photon could travel was incredibly short. This is known as the mean free path of the photon. Some calculations suggest a photon could travel only a few hundred light years. For comparison, the nearest galaxy to our Milky Way is over 2 million light years away. A photon needing to cross intergalactic space would be absorbed thousands of times. The universe was effectively opaque to all ultraviolet light. Hot young stars are known to produce enormous amounts of ultraviolet radiation. That is their primary form of energy output when they are young. If all of that UV light gets absorbed immediately by the surrounding hydrogen, the stars would remain completely invisible to any distant observers. Any galaxy in the early universe would be cloaked by this cosmic fog. It would be impossible to see it from outside its local neighborhood. The only way that light can escape is if the hydrogen gets ionized. Ionized hydrogen is hydrogen that has lost its single electron. Without an electron, it cannot absorb photons in the same way. Ionized hydrogen is essentially transparent to light. But ionizing all of the hydrogen throughout the universe requires enormous energy. This process is known as the epoch of reionization. It began when the first stars and galaxies started to form. They produced enough UV radiation to ionize bubbles of hydrogen around them. Gradually, these ionized bubbles began to expand and merge. Eventually, after several 100 million years had passed, most of the hydrogen in the universe had been reionized. The cosmic fog finally lifted, and light could travel freely again. Current estimates suggest that reionization was substantially complete. It was complete by about 1 billion years after the Big Bang. It may have started much earlier than that, however. The 300 mysterious galaxies existed during this transition, or they may have existed possibly before reionization even finished. This means that they were shining into a universe still partially filled with fog. Some of their light should have been absorbed by this fog, yet we are able to detect them clearly with the James Webb Space Telescope. Either they formed in regions where reionization happened unusually early. This would have created clear pathways for their light to escape, or they were so incredibly luminous that they remained visible. They were visible even with a substantial amount of absorption. Their brightness might have itself contributed to the reionization process. If these 300 objects were as luminous as they appear, They would have pumped enormous amounts of UV radiation into their surroundings. That radiation would have ionized the nearby hydrogen gas. It would have carved out large, transparent zones around them. If enough of these galaxies existed across the entire universe, they could have collectively driven reionization much faster than our models predict. But that creates a kind of circular problem for us. We think that they are visible because reionization happened, but reionization might have happened because they existed. So which of these two things actually came first? The hydrogen fog should have trapped all of their light. The fact that we are able to see them at all suggests something unusual. Something unusual about either these objects or the state of the universe at that time. The Hubble Space Telescope operated for over 3 decades. It captured some of the most iconic images in the history of astronomy. It peered deep into the universe, revealing distant galaxies, galaxies that are billions of light years away from us. It studied the cosmic dawn and found some of the first galaxies, galaxies forming hundreds of millions of years after the Big Bang. Yet, Hubble never saw the 300 mysterious objects. These are the objects that the James Webb Space Telescope discovered. Why did the most powerful telescope of its generation miss them? The answer to this question lies in the wavelength of light. Hubble primarily observes ultraviolet, visible, and near-infrared light. Its instruments cover wavelengths from about 120 nanometers. This goes all the way up to 1600 nanometers. This range is perfect for studying nearby galaxies. It is also good for studying moderately distant objects. But extremely distant galaxies have their light severely redshifted. Light that left them as ultraviolet or blue visible light gets stretched. It gets stretched by cosmic expansion until it arrives as infrared radiation. For galaxies at redshifts above 7, much of their light is shifted. It is shifted beyond the detection range of the Hubble Space Telescope. James Webb was specifically designed to overcome this very limitation. Its instruments can cover wavelengths from 600 nanometers. They go all the way out to 28,000 nanometers. That is deep into the mid-infrared part of the spectrum. Webb can see light that has been stretched far beyond Hubble's capabilities. Think of it as being like tuning a radio to a different station. Hubble was tuned to one specific set of frequencies. Webb is tuned to a different, longer set of frequencies. The same objects might be transmitting on both of these frequencies, but the signal will be much stronger at the wavelength each telescope is designed for. For extremely distant galaxies, Webb's infrared sensitivity is absolutely essential. Hubble did observe some of the same regions of the sky, regions where Webb found the 300 mysterious objects. The Cosmic Evolution Early Release Science Survey provided much of the data. It focused on an area that Hubble had previously studied in depth, but Hubble's images of that area showed either nothing at all, or they showed extremely faint smudges where Webb revealed bright red galaxies. This is not a failure of the Hubble Space Telescope. It is a fundamental limitation of the physics of light. You cannot detect light at wavelengths your instruments are not sensitive to. No amount of exposure time or clever processing could make Hubble see this. The photons that are arriving from these distant galaxies are outside its range. Webb also has another significant advantage over Hubble. That advantage is its much larger size. Its primary mirror measures 21 feet across. This is compared to Hubble's much smaller 8-foot mirror. Larger mirrors are able to collect more light. This allows them to detect much fainter objects. Webb is about 6 times better at collecting light than Hubble is. This sensitivity boost makes an enormous difference. It is especially important when observing extremely faint, distant galaxies. The combination of infrared sensitivity and a large mirror allows Webb to see things. It can see objects that were essentially invisible to Hubble. The 300 candidates were hidden in plain sight. They were broadcasting their presence at wavelengths that Hubble could not detect. Some astronomers had predicted that this would happen. Before Webb was launched, theoretical models suggested this. numerous distant galaxies might exist beyond Hubble's detection limits. But the predictions underestimated how many and how bright they would be. Webb found more candidates and brighter ones than most models anticipated. Interestingly, Hubble did detect a few very distant early galaxies. It found some objects at redshifts around 7 to 8. But these were small, faint systems with much less stellar mass. They had much less mass than the 300 Webb discovered. They fit the expectations of the time perfectly. They were the small baby galaxies that astronomers expected to find. Webb's new discoveries represent a completely different population. These are larger, brighter, and more mature than anything Hubble could see. They are pushing into mass ranges that should not exist so early. Hubble gave us our first glimpse of the cosmic dawn. Webb is now revealing that this dawn was far brighter and more active. It was more active than we had ever imagined it to be. The fact that Hubble missed these objects is not surprising in retrospect. What is truly surprising is that they exist at all. Imagine trying to build a massive skyscraper, but you only have access to enough steel and concrete for a small house. That is essentially the problem that these early galaxies present. The amount of matter that was available in the infant universe was limited, yet some of these 300 objects appear to contain enormous stellar masses that are equivalent to tens or even hundreds of billions of suns. Where did all of that incredible mass come from so early? After the Big Bang, the universe consisted mostly of hydrogen and helium gas. About 73% of it was hydrogen. About 25% of it was helium. There were also tiny traces of the element lithium. Dark matter made up about 84% of the total matter. But dark matter cannot form stars, as it does not interact with light. Only the ordinary matter could collapse into stellar objects. This gas was spread relatively thinly across the vastness of space. The average density of matter in the universe was incredibly low, though it did vary from place to place due to quantum fluctuations. The denser regions would eventually become the galaxies we see today. But even in these denser regions, gathering enough gas takes time. It takes a long time to build a massive galaxy from scratch. Modern large galaxies like the Milky Way contain a lot of stars. They contain about 100 to 400 billion solar masses of stars, but they did not acquire all of this mass at once. They accumulated it over billions of years of time. They did this through continuous star formation and by merging. They merged with many smaller galaxies over their lifetimes. Each of these mergers added more mass to the growing galaxy. The entire process was very slow and gradual. For the 300 early candidates to possess comparable masses, to do so within just 500 million years is a problem. They would have needed to gather material at extraordinary rates. Gas from a large volume of space had to be funneled into small regions. The infall rate of this gas must have been 10 to 20 times higher than what is seen in modern galaxies today. Dark matter halos can help to facilitate this process. Their immense gravity pulls the ordinary matter inward, but as we discussed, sufficiently massive dark matter halos should not have formed yet. The halos that did exist at that time were much smaller. They were only capable of supporting small dwarf galaxies. One possibility is that these objects formed in rare, extremely dense regions where the concentration of matter was unusually high. Statistical fluctuations in the initial density field mean some regions were denser. If a galaxy formed in one of these rare peaks, it would have more gas. But this explanation can only go so far in solving the problem. Even the densest regions in our standard cosmological models do not provide enough. They do not provide enough excess matter to explain these masses so early. You would need density enhancements exceeding what random fluctuations produce. Another factor to consider is the gas accretion efficiency. Modern galaxies are known to be quite wasteful with their gas. Much of the gas that falls into a dark matter halo never becomes stars. Feedback from stellar winds and supernovas heats the gas. or it blows the gas out of the galaxy entirely. Only a small fraction of the available gas actually forms stars. If the early galaxies had a much higher efficiency, if they converted a larger percentage of inflowing gas into stars, they could have built up their mass much faster. Perhaps the feedback mechanisms were less effective in the early universe. The gas was much denser and more pristine, which might have helped. It might have allowed for more efficient star formation before feedback kicked in. Rapid mergers could also have contributed to their rapid growth. If multiple proto-galaxies formed close together and quickly merged, their combined mass would create a much larger system. Instead of one galaxy slowly growing over time, several small ones would have joined forces very early on. This would require special circumstances, but it could have happened. It could have happened in the densest regions of the early universe. There is also the possibility that some of these objects are not as massive. They might not be as massive as they appear to be. If they are actually quasars, or black hole-powered systems, the extreme luminosity might be misleading the mass estimates. A bright quasar could mimic the appearance of a galaxy that contains billions of stars, while it is actually a much smaller system in reality. But if even a fraction of the 300 candidates are genuine, if they are genuinely massive early galaxies, the mass mystery remains. The universe somehow concentrated billions of solar masses of gas. It concentrated it into small regions and converted much of it to stars. It did this within an impossibly short amount of time. The logistics of this simply do not add up using our standard physics. Something about the early universe's mass distribution must be different, or the efficiency of galaxy formation must be different than our models assume. Determining how far away something sits in the universe is hard. It sounds straightforward until you actually try to do it. There are no cosmic mile markers or distance signs in space. Everything that astronomers know about distances comes from analyzing light. And for the 300 mysterious objects, getting those distances right is critical. Cosmological redshift is the key measurement for this. As space expands, it stretches the light that is traveling through it. The amount of this stretching directly relates to how much the universe has expanded. It has expanded since the light was first emitted. More expansion means more stretching of the light's wavelength. More stretching means a higher redshift value. A higher redshift means we are looking farther back in time. Astronomers express redshift as a number that is called Z. A galaxy that is at redshift 0 is right here, right now. A galaxy at redshift 1 existed when the universe was half its current size. At a redshift of 7, the universe was 1/8 of its present size. At a redshift of 10, it was 1/11 of its current size. These fractions tell us how much expansion occurred between then and now. The 300 candidates show a wide range of estimated redshifts. Initial analysis using the dropout technique suggested they were distant. Many might sit at redshifts above 7 a very early time. This means they existed less than 800 million years after the Big Bang. But these dropout estimates are only approximate values. They provide ballpark figures, not precise scientific measurements. The spectral energy distribution fitting helped to refine these estimates. By comparing the observed brightness across multiple wavelengths to models, astronomers were able to narrow down the likely redshift ranges. About 2/3 of the objects appear to sit at lower redshifts. Redshifts between 1 and 4, which is a later time. This is still distant, but not impossibly early in cosmic terms. These closer objects are interesting, but they do not break our models. The remaining 100 or so candidates, however, were different. They showed spectral energy distributions consistent with very high redshifts above 7, with some potentially reaching 10 or higher. If these estimates are correct, these objects existed when the universe was young, when it was between 3 and 5% of its current age. They are witnesses to the very infancy of the cosmos. But there is a great deal of uncertainty in these measurements. The SED fitting relies on models that might not be perfect. If these early galaxies had unusual properties not included in the models, the derived redshifts for them could be wrong. An object that is thought to be at redshift 10 might actually be at redshift 5. That is where the technique of spectroscopy becomes absolutely essential. Unlike broad filter imaging, spectroscopy dissects the light. It spreads the light out into a detailed rainbow of colors. It reveals absorption and emission lines from specific atoms. Each element produces these lines at known wavelengths when at rest. By measuring how much those lines have been shifted, astronomers can determine the exact redshift with much greater precision. For example, the element hydrogen produces a strong emission line. It is at 656 nanometers when at rest. This is called the H-alpha line of hydrogen. If a galaxy's H-alpha line appears at 1312 nanometers, this is exactly double the rest wavelength of the line. The redshift of that galaxy is exactly 1. The line has been stretched by a factor of 2 by cosmic expansion. This means the universe has expanded by a factor of 2 since the light was emitted. Spectroscopy can also reveal what is producing the light. Stars have characteristic spectral signatures that are different from gas clouds. Active galactic nuclei show strong emission lines from hot gas. Quasars have very different spectral signatures from normal galaxies. By examining the detailed spectrum of an object, astronomers can confirm whether it is truly a galaxy or something else. The chemical composition of a galaxy also comes from spectroscopy. The relative strengths of the different spectral lines indicate the elements. They tell us which elements are present and in what quantities. Early galaxies should show what is known as low metallicity. This means they have very few heavy elements in them. They formed from gas that was nearly pure hydrogen and helium. If a supposed early galaxy shows a high metallicity, it is probably not as ancient as it appears to be. Stellar population age estimates also improve dramatically with spectroscopy. Absorption features from certain elements only appear in stars of specific ages. Young stars show very strong hydrogen lines in their spectra. Old stars show molecular absorption bands in their spectra. By analyzing the full spectrum of a galaxy, astronomers can determine the mix of stellar ages within it. They can also estimate when most of the stars in it formed. The challenge is that spectroscopy requires more observation time. You need to collect the light for many hours or even days. This is necessary to build up a strong enough spectrum for analysis. With hundreds of candidates to follow up on, this is a massive undertaking. It represents a huge commitment of valuable telescope time. Priority is being given to the brightest and most interesting targets. Astronomers are currently planning spectroscopic observations of dozens of the candidates. These observations will confirm their distances and reveal their compositions. They will also determine the nature of their stellar populations. Within the next year or two, we will know for certain. We will know which of these objects are genuinely ancient, and we will know which of them are just imposters. Until then, the redshift measurements remain provisional. But even these provisional estimates are shocking enough to demand our attention. Stars do not just form instantly in the universe. The process follows specific physical rules with speed limits, yet the 300 early galaxies appear to have violated these limits. They created their stars much faster than physics should allow. Understanding why this is a problem requires looking at what regulates star formation. In modern galaxies, star formation happens in cold, dense molecular clouds. These clouds contain mostly hydrogen molecules with very low temperatures. Temperatures around -440 degrees Fahrenheit. Gravity slowly compresses the densest parts of these clouds. As the material falls inward, it begins to heat up. When the center of the cloud reaches about 18 million degrees, nuclear fusion finally ignites and a new star is born. This collapse process typically takes about 10 million years. It goes from an initial clump of gas to a newborn star. That might sound fast, but it imposes limits on how quickly a galaxy can grow. If each star takes 10 million years to form, and you are forming them one at a time, it takes a long time. Building billions of stars in this way would take billions of years. Real galaxies form many stars simultaneously in different regions. A single molecular cloud might spawn hundreds or thousands of stars. It does this over a period of just a few million years. Multiple clouds across the galaxy are forming stars at the same time. This parallelization speeds up the process considerably, but there are still significant constraints on this process. The main one is the process of stellar feedback. Massive young stars produce incredibly intense radiation. This radiation heats the surrounding gas in the cloud. This heat increases the gas pressure, which opposes gravity. The heated gas becomes much harder to compress into new stars. Massive stars also drive powerful stellar winds of particles. These winds can blow the gas away from the star-forming regions. When massive stars die as supernovas, the explosions are immense. They inject enormous amounts of energy into the surrounding environment. This energy heats, disperses, and ionizes the nearby gas. For a while after a supernova star formation in that region stops, the gas needs time to cool down and settle before it can form stars again. These feedback mechanisms keep the star formation rates in check. Even the most active starburst galaxies in the modern universe rarely exceed a certain rate. They rarely exceed 100 solar masses per year. Most typical galaxies form stars at much lower rates, between 1 and 10 solar masses of stars annually. The feedback acts like a kind of cosmic thermostat. It prevents any runaway star formation from occurring. Now consider what the early candidates seem to have accomplished. If they truly contain 50 to 100 billion solar masses of stars, and they built these populations in just 500 million years, the average star formation rate must have been 100 to 200 solar masses per year, and this rate must have been sustained for 500 million years. That is already at the extreme end of what we observe today. But remember, these rates also need to account for stellar deaths. Massive stars only live for a few million years. They then die and stop contributing to the total stellar mass. To maintain a growing stellar population over time, you need to form stars much faster than they are dying. When you factor in the stellar death rates for these galaxies, the required star formation rates jump even higher. Some estimates suggest these galaxies needed to sustain extreme rates of 300 to 500 solar masses per year. This would have been during their peak growth periods, that is 3 to 5 times higher than the most extreme starbursts today. How do you achieve such incredibly high rates of star formation? How do you do it without feedback shutting everything down? One possibility is that feedback was less effective in the early universe. The gas was much denser and more gravitationally bound. It might have been able to resist being blown away. It could have resisted despite intense stellar winds and supernovas. Another idea involves the efficiency of star formation. Maybe the first stellar populations formed in unusually efficient bursts. Large percentages of the available gas could have been converted to stars. This would have happened before the feedback kicked in. Instead of the typical few percent efficiency that is seen today, early galaxies might have achieved 10 or 20% efficiency. There is also the possibility of a sustained inflow of gas. If gas was continuously streaming into these galaxies from their surroundings, star formation could have continued even as feedback expelled material. The expelled gas would have been replaced by fresh inflowing gas. This requires special geometric configurations or density distributions. These are not common in the modern universe we see around us. Some astronomers suggest the star formation might not have been steady. Instead of constant rates, these galaxies might have had multiple bursts. These bursts would be separated by quiet periods of time. Each burst would have converted enormous amounts of gas to stars. It would have done so over just a few million years. Multiple bursts could have built up the large stellar populations. They would have done so without requiring sustained extreme rates. But even these burst scenarios struggle to match the observations. The bursts would need to be incredibly intense to work. They would also need to occur frequently enough to build the required mass. Whatever mechanism drove the star formation in these early galaxies, it operated far beyond our current understanding of the process. The universe underwent one of its most dramatic transformations. It happened between 400 million and 1 billion years after the Big Bang. During this era, which is called the epoch of reionization, the neutral hydrogen that was filling all of space became ionized again. The cosmic fog that had pervaded the universe finally lifted. Light could then travel freely for the first time since the Dark Ages. The 300 galaxies should have been a part of this process. Instead, they might have finished their formation before it even started. Understanding reionization requires knowing what needed to change. After recombination 380,000 years after the Big Bang, hydrogen existed as neutral atoms with electrons bound to protons. This neutral hydrogen was very good at absorbing ultraviolet light. This is what made the universe opaque during that time. For reionization to occur, something needed to strip the electrons away. It needed to strip them from the hydrogen atoms throughout all of space. That something was the ultraviolet radiation from the first stars and galaxies. Hot young stars are known to produce copious amounts of UV photons. These photons are energetic enough to ionize the hydrogen atoms. Each UV photon can knock an electron off of a hydrogen atom. As more and more stars formed, more UV radiation flooded the universe. Gradually, bubbles of ionized hydrogen began to expand around each galaxy. These ionization bubbles grew larger, and they eventually merged. Over time, they overlapped and filled most of space with ionized hydrogen. The transformation of the universe was not an instantaneous process. It took several 100 million years for the universe to transition. It went from being mostly neutral to being mostly ionized. Current estimates suggest that reionization was substantially complete by 1 billion years. It was complete 1 billion years after the Big Bang. The 300 mysterious galaxies existed during or before this transition. If they formed at 500 to 700 million years after the Big Bang, they were shining when the universe was still significantly neutral. Their light had to be able to punch through the remaining hydrogen fog. It had to do this in order to reach us here on Earth. But here is where things start to get very interesting. If these objects were as bright and numerous as they appear to be, they should have contributed massively to the reionization of the universe. 300 bright galaxies pumping out UV radiation would ionize a lot of hydrogen. If similar populations of these galaxies existed across the entire sky, not just in the regions that have been surveyed so far, thousands of such galaxies might have existed at that time. Collectively, they could have driven the reionization process much faster and earlier than our current models of cosmology predict. Some simulations have suggested that if massive galaxies formed so early, and if they formed as abundantly as the Webb observations hint, reionization could have been substantially complete by 600 million years. 600 million years after the Big Bang, which is very early. That is 400 million years earlier than the standard estimate. But an early reionization creates its own set of problems. We have observational constraints on when reionization occurred. Astronomers studied distant quasars whose light passed through the universe. It passed through when the universe was still partially neutral. The quasar light shows absorption features from the neutral hydrogen. This allows researchers to map how much neutral hydrogen existed at different times. These observations suggest that significant neutral hydrogen remained. It remained until at least 800 million years after the Big Bang. Reionization was not finished early according to this data. It proceeded more or less on the timescale that our standard models predict. If the 300 galaxies existed and were as bright as they seem, why did they not reionize the universe much faster? One possible answer is that most of their UV radiation never escaped. Perhaps the dust within these galaxies absorbed the UV photons. It would have absorbed them before they could ionize the surrounding hydrogen. Or maybe the galaxies were surrounded by especially dense neutral hydrogen. This hydrogen would have absorbed the UV radiation in their immediate vicinity. This would have prevented it from reaching the intergalactic space. Another possibility is that these objects are not as numerous as they seem. The surveyed area represents a very tiny fraction of the entire sky. Maybe the researchers just happened to observe an unusually dense region. If so, the actual number of such galaxies across the whole universe would be lower. They would have produced less UV radiation overall, or perhaps their redshift estimates are simply wrong. If most of the candidates actually sit at lower redshifts, they would have existed later in cosmic history. They would have existed when reionization was already underway or complete. They would not need to contribute to the early reionization. This is because they simply were not there yet to do so. The alternative idea is much more radical in its implications. Maybe reionization did proceed faster than we think it did, but it happened in a very uneven and patchy way. Large regions of the universe could have become fully ionized early on, while other regions could have remained neutral for much longer. The observational constraints we have come from specific lines of sight to very distant quasars in the universe. Those sight lines might just be passing through regions that stayed neutral longer. Reionization is one of the least understood epochs in all of cosmic history. We have some observational hints, but we do not have complete data yet. The 300 galaxies add another puzzle piece to this picture, but it is not yet clear where this new piece fits into the overall puzzle. Either they contributed to reionization in ways we do not fully understand, or they existed in a universe that was already more ionized than we realized. Every field of science has a foundational framework, a set of rules that explains how things work in that field. In the field of cosmology, that framework is called ΛCDM. It has stood as our best explanation for cosmic evolution for decades. The 300 galaxies that James Webb discovered might require rewriting it. Understanding what is at stake requires knowing what ΛCDM actually says. The lambda part of the name refers to dark energy. This is the mysterious force that is accelerating the universe's expansion. The CDM part stands for cold, dark matter. This is the invisible substance that provides the gravitational scaffolding for structure, together with ordinary matter radiation and the laws of general relativity. These components create a model that explains most of our observations. ΛCDM makes very specific predictions about how structure forms over time. In the beginning, matter was distributed almost uniformly. There were only tiny density variations from place to place. These variations came from quantum fluctuations during inflation. Over time, gravity amplified these tiny variations. The denser regions pulled in more matter, becoming denser still. The model predicts what is known as a bottom-up growth pattern. Small structures are the first things to form in the universe. Dwarf galaxies assemble within a few 100 million years after the Big Bang. These dwarfs then merge over time, building progressively larger galaxies. Giant galaxies like our own Milky Way do not fully assemble until later, not until several billion years have passed in the universe. The timeline for this process is hierarchical and relatively slow. ΛCDM also predicts how many galaxies of each mass should exist. It predicts this for different times in cosmic history. Early in cosmic history, you should find many small galaxies, and you should find very few large ones. As time progresses, the number of large galaxies increases. It increases through the process of mergers between smaller galaxies. By calculating how structure grows under the influence of gravity, cosmologists can predict the mass distribution of galaxies at any epoch. These predictions have been tested extensively by astronomers. Surveys of nearby galaxies match the ΛCDM expectations very well. Observations of the cosmic microwave background also agree with the model. This is the oldest light that we can possibly see. For many decades, ΛCDM has successfully explained our observations, but the 300 early galaxies are challenging this success, if even a fraction of them are genuinely massive and ancient. They exist in numbers that ΛCDM simply does not predict. The model says that massive galaxies should be extremely rare. They should be rare 500 million years after the Big Bang. Finding hundreds of them in a relatively small survey area suggests something. It suggests that they are not rare at all. There are several possible resolutions to this problem. The simplest one is that most of the candidates are not at high redshift. If their distances were overestimated, they are not as early or problematic. Follow-up spectroscopy might reveal that many of them sit at lower redshifts. This is where ΛCDM can comfortably accommodate them. Another possibility is that ΛCDM is mostly correct, but it might be missing some important details. Maybe dark matter is not entirely cold as we assume. Perhaps it has a warm component that speeds up structure formation. Or maybe the initial density fluctuations from inflation were larger than we thought in some rare regions of the universe. This would allow for faster galaxy growth in those areas. A more significant change would involve the physics of star formation. ΛCDM focuses on dark matter and large-scale structure. It does not model the detailed processes of star formation within galaxies. If star formation was more efficient in the early universe than we assume, galaxies could have built up their stellar mass much faster. They could have done this without violating the dark matter framework. The most radical resolution is that ΛCDM needs fundamental revision. Maybe dark matter behaves differently than we currently think. Perhaps dark energy was stronger or weaker in the early universe, or possibly general relativity itself needs to be modified. Most cosmologists are not ready to abandon ΛCDM just yet. The model has had too many successes to be discarded so easily, but they are definitely concerned about these new findings. If spectroscopy confirms that many of the candidates are genuinely at high redshift, and they are genuinely massive galaxies for that epoch, ΛCDM will require some significant adjustments. Joel Leyer put it directly in a recent statement. Finding these objects challenges our current ideas about how galaxies formed, how they formed in the very early universe. The emphasis on the word challenges is polite scientific speak. It means that this does not fit what we expected at all. The next few years will determine whether ΛCDM survives intact, or if it requires significant modifications to its framework, or if it faces a crisis that demands entirely new physics. The 300 galaxies are forcing cosmologists to confront uncomfortable questions about their most successful and long-standing theory. What if the impossible galaxies had some help from the universe's earliest moments? Some cosmologists are exploring a very radical new idea. Maybe primordial black holes seeded the growth of these massive galaxies. These are objects that would have formed during the first seconds after the Big Bang. It sounds like something out of science fiction, but the physics behind the idea might actually work. Primordial black holes are very different from the black holes we normally discuss. Regular black holes form when very massive stars collapse. That process requires that stars must exist first. Primordial black holes would have formed in a different way. During the first fraction of a second after the Big Bang, density fluctuations in the expanding universe could have been strong enough to create black holes directly from compressed energy. These primordial black holes could have had any mass. Some of them might have been tiny, weighing less than a mountain. Others could have been enormous, containing thousands of solar masses. Unlike stellar black holes that take millions of years to grow, primordial black holes would have existed from the very beginning. They would have been already massive from the start. Now imagine one of these primordial black holes sitting in a dense gas cloud. a gas cloud during the cosmic dark ages. The black hole's immense gravity would pull the gas inward. As the gas spirals into the black hole, friction heats it up. The hot gas would radiate enormous amounts of energy. This radiation would heat and ionize the surrounding gas. This would affect the nearby star formation in the region. The energy from the black hole could actually trigger star formation. Compression waves from the heated gas might cause cold gas to collapse. It would collapse into stars at a much greater distance. At the same time, gas closer to the black hole would be dispersed. This would create a complex pattern of enhanced and suppressed star formation. Primordial black holes could also have acted as gravitational anchors. Their mass would have helped to pull matter into dense concentrations. They could have done this much faster than dark matter alone. A million solar mass black hole sitting at the center of a proto-galaxy. It would significantly boost the rate at which gas falls inward. More gas means more stars can form over the same period of time. This mechanism could explain how massive galaxies assembled so quickly. Instead of waiting for dark matter halos to slowly build up, these galaxies had primordial black holes to jumpstart the process. The black holes would have provided both gravitational anchors and energy sources. This would have accelerated the galaxy formation process. There is some indirect evidence that supermassive black holes existed very early. Webb and other telescopes have found quasars at high redshifts. These are extremely bright objects powered by supermassive black holes. They are found at redshifts above 7 in the early universe. These black holes contain millions or billions of solar masses. Growing them from stellar mass seeds in the available time is challenging. Primordial black holes offer an alternative origin for them. If primordial black holes did seed the early galaxies, it could explain several of their puzzling features. The extreme brightness of some of the early objects makes sense. It makes sense if they contain actively feeding central black holes. The rapid mass assembly of these galaxies works well. It works if the black hole's gravity accelerated the gas infall. Even the unusual colors of these objects could be a result of black hole activity. The black hole activity could be heating the surrounding dust, but there are some significant problems with this particular idea. We do not have any direct evidence that primordial black holes exist. They are theoretically possible, but they have never been confirmed. Detecting them is extremely difficult because they do not emit light. They do not emit light unless they are actively feeding on matter. Most of them might be dark and completely invisible. They could be drifting through space completely undetected. Also, primordial black holes should be extremely rare, if they exist at all in the universe. Current constraints from various observations suggest this. Only a tiny fraction of dark matter could be in the form of primordial black holes. Having hundreds of early galaxies that were seeded by them is unlikely. It would require that primordial black holes are more common than we think, or that we got very lucky in where we pointed the James Webb telescope. Another issue is that black hole activity should produce specific signatures. Active feeding black holes are known to create X-rays. They also create strong emission lines and powerful jets. Some of the 300 candidates do show hints of these features, but many of them do not show any of these signatures. If primordial black holes seeded all of them, why do they not all show the signatures of black holes? The idea remains speculative, but it represents creative thinking. It represents the kind of creative thinking that astronomers are pursuing. When observations do not fit our standard models, you have to explore all of the different alternatives. Primordial black holes might not be the final answer, but investigating the possibility could reveal new insights. Insights about the very early universe and its evolution. Sometimes the most unlikely ideas can turn out to be correct. Right now, astronomers are keeping all of their options on the table. Not all of the mysterious early objects are blazing with star formation. Some of them apparently went dormant remarkably early on. They shut down their stellar assembly lines while the universe was still in its infancy. Astronomers have nicknamed these objects sleeping beauty galaxies, and they are almost as puzzling as the actively forming ones. A dormant galaxy is one that contains stars but is not creating new ones. All of its gas has either been consumed, expelled, or heated up. Heated so much that it can no longer collapse to form stars. The galaxy's stellar population then ages quietly without any replacement. In the modern universe, dormant galaxies are very common. Many massive elliptical galaxies stopped forming stars billions of years ago, but finding them in the very early universe is quite shocking. The first sleeping beauty was discovered in data predating the Webb candidates. Astronomers found a galaxy that existed just 680 million years after the Big Bang, and it showed no signs of any ongoing star formation. Its spectrum revealed that it contained very old stars, stars with ages that suggested they had formed even earlier. The galaxy had built up its stellar population very quickly. Then, for some inexplicable reason, it had simply stopped. Since that initial discovery, more of these sleeping beauties have turned up. Some of the 300 candidates that Webb found might be dormant. They might be dormant rather than actively forming new stars. Their extreme redness could indicate the presence of old stellar populations. It would not be due to the presence of dusty young ones. Distinguishing between these two interpretations requires detailed spectroscopy. Why would a galaxy stop forming stars so early in its life? In the modern universe, we understand several quenching mechanisms. A supermassive black hole at the galaxy's center can heat the gas. This heating prevents the gas from cooling and forming new stars. Mergers between galaxies can disrupt their gas supplies. Ram pressure from moving through intergalactic gas can strip a galaxy. It can strip it of its fuel for star formation. But these mechanisms should not work effectively in the early universe. Supermassive black holes take a great deal of time to grow. They were probably not massive enough yet to heat and expel large amounts of gas. The intergalactic medium was much thinner back then. This would make ram pressure stripping a much less effective process. Mergers could have disrupted the gas temporarily, but they should not have permanently quenched the star formation. Not in such a gas-rich environment as the early universe. There is also the difficult problem of the timing. These galaxies apparently formed most of their stars very early. They did so within the first few 100 million years. The rapid formation that we have discussed makes sense. It makes sense if gas was available and collapsing efficiently. But what changed in these systems to suddenly halt the process? One idea involves the feedback from the first generation of stars. If an intense burst of massive stars formed all at once, their combined supernovas could have created a powerful shockwave. A shockwave that was powerful enough to blow most of the remaining gas out. Without any gas left, the star formation would have stopped, but the galaxy would need to retain the gas it had already converted to stars, while at the same time losing all of the rest of its gas. That is a very delicate balance to achieve in practice. Another possibility is that environmental effects played a role. Maybe these sleeping beauties formed in regions that became depleted of gas, depleted unusually quickly for some reason. Nearby galaxies or other energetic events might have consumed the gas, or they might have ionized the available hydrogen, starving these galaxies. Some astronomers have suggested that the sleeping beauties are not truly dormant. They might just be taking a temporary break from star formation. They could be going through cycles of active star formation, followed by quiet periods where nothing much happens. What we are seeing is just a temporary pause in their activity. Given another few 100 million years, they might reignite. They could reignite their star formation when fresh gas becomes available. The sleeping beauties also raise questions about how common they are. If a significant fraction of early galaxies went dormant so quickly, it would affect our understanding of how stellar mass accumulated over the entire history of the universe. Mass that is locked up in dormant galaxies does not contribute. It does not contribute to later star formation or galaxy growth. It represents a kind of dead end in the evolutionary tree. Some of these objects have shown signs of possible rejuvenation. They have shown this in later observations of them. A galaxy that was dormant at a redshift of 8 might show new star formation. It might show this by the time it reaches a redshift of 6. The sleep is not necessarily a permanent state for them, but the fact that they could go dormant at all so early in cosmic history, it challenges our assumptions about how galaxy evolution proceeds. Finding these sleeping beauties was not at all expected. Neither was finding 300 extremely bright, actively forming galaxies. The early universe appears to be far more diverse than our models predicted. Some galaxies were forming stars at impossible rates. Others somehow formed their stars briefly and then just stopped. The wide variety suggests that galaxy formation was a complex process, a process that we do not yet fully understand. The sleeping beauties are teaching us that early galaxies did not follow a single path. Multiple different formation mechanisms might have been operating at the same time, and these different mechanisms could have produced very different outcomes. Among the 300 mysterious objects that were discovered, 3 of them stand out as being particularly impossible. Astronomers discovered these red monsters in a separate study. They were also using data from the James Webb Space Telescope. They are so massive and so early that they make the other candidates look reasonable. They look almost reasonable by comparison to these 3. Each of them contains stellar populations that rival the largest galaxies that we see in the modern universe. Yet they existed just 700 million years after the Big Bang. The 3 red monsters are sitting at redshifts around 7 to 8. That places them in the era when reionization was still ongoing, when most galaxies should have been small and still developing. Instead, these objects contain estimated stellar masses of huge proportions, between 80 billion and 200 billion solar masses each. For comparison, our own Milky Way galaxy contains about 150 billion solar masses. Finding just one such massive galaxy at that early epoch would be surprising. Finding 3 of them in a relatively small survey suggests something. It suggests they might not be as rare as our theories predict. If the surveyed area contains 3 of these objects, how many of them might exist across the entire observable universe? The number could potentially be in the thousands. What makes these red monsters especially problematic is their efficiency. Galaxies are known to form their stars from gas, but not all of the available gas in a galaxy becomes stars. Most modern galaxies only convert about 10 to 20% of their gas. The rest of the gas either never collapses to form stars, or it gets expelled from the galaxy by feedback processes. This low efficiency is the reason why galaxy formation is so slow. The 3 red monsters apparently converted their gas to stars with incredible efficiency. Calculations suggest they turned 40 to 50% of their available gas into stars. That is an unprecedented level of star formation efficiency. No galaxy in the modern universe is known to achieve such high efficiency. These objects somehow manage to bypass the feedback mechanisms, the mechanisms that normally prevent such efficient star formation. Stein Weitz, an astronomer who is studying these objects, described them. He described them as posing a tantalizing puzzle for us. Many processes in galaxy evolution are known to introduce rate-limiting steps. Stellar feedback is known to heat the gas in galaxies. Supernova explosions can disperse the material needed for star formation. Black hole activity can also shut down star formation entirely. Yet these red monsters seem to have evaded most of these hurdles, and they built up enormous stellar populations at a breakneck speed. The term red monster comes from their extreme color. Like the other candidates, they glow a deep red in the infrared images. Their spectral energy distributions suggest they are dusty, mature systems. They seem to have large populations of old red stars. Some of them might even be partly dormant already. They could have already gone through their most active star-forming phase. If these objects formed through the standard hierarchical process, they would represent the merger of dozens or hundreds of smaller proto-galaxies. But there simply was not enough time for that many mergers to have occurred. At 700 million years after the Big Bang, the universe barely had enough time for 1 or 2 major merger events per system. Building such massive galaxies in this way would require continuous mergers happening much faster than our simulations predict. The alternative is that they formed through a more direct collapse process. Instead of gradually assembling from many small pieces over time, they might have formed when massive gas clouds collapsed almost all at once. This top-down formation contradicts ΛCDM's bottom-up predictions, but the observations seem to demand this kind of explanation. The 3 red monsters also raise some serious questions about dark matter. To support such massive galaxies, they would need massive dark matter halos. These halos would need to contain at least 1 trillion solar masses of dark matter. Building such massive halos within just 700 million years is a problem. It pushes the very limits of what our cold dark matter models allow. Some researchers have wondered if we are just seeing statistical flukes. Maybe these 3 galaxies just happen to form in an unusually dense region, a region where the conditions favored extremely rapid growth. The universe is large enough that rare events can occasionally happen. Perhaps we are just witnessing an extremely improbable configuration, a configuration that should not be generalized to other regions. But finding 3 such objects in a single survey seems like too many coincidences. If they were truly rare, 1 in a billion occurrences, we should not have found any of them in the surveyed area. Finding 3 of them suggests that they are uncommon but not impossibly rare. And if they are not impossibly rare, our cosmological models need to explain them. They need to explain how these objects can form so early. The red monsters have pushed already strained theories to their breaking point. They are not just challenging the details of galaxy formation models. They are questioning fundamental assumptions about how quickly massive structures can assemble, how quickly they can assemble in the early universe. These 3 objects might represent the most extreme examples yet found, but they are probably not alone in the vastness of the early cosmos. The story that we have told about the universe's earliest galaxies is changing. For many decades, our textbooks have painted a picture of gradual growth, small galaxies slowly merging into larger ones over billions of years. The first chapter of cosmic history described a universe emerging slowly from darkness and cautiously building its first structures. The 300 galaxies that James Webb discovered are forcing us to change this. They are forcing us to rip out that chapter and start all over again. Here is what we thought we knew about the early universe. After the cosmic dark ages ended around 400 million years after the Big Bang, the very first stars in the universe began to form. These primordial stars were isolated giants scattered sparsely through space. Over the next few 100 million years, they began to cluster together. They formed small proto-galaxies containing perhaps 10 to 100 million stars each. These dwarf galaxies were the fundamental building blocks of the cosmos. They would merge with each other in a pairwise fashion. They would combine their stellar populations over time. 2 dwarf galaxies would merge to make a slightly larger galaxy. That larger galaxy would then merge with another one growing incrementally. The process resembled a kind of cosmic construction project, carefully assembling a massive structure piece by piece. By 1 billion years after the Big Bang, modest galaxies started appearing. Truly large galaxies would not exist for several billion more years. This particular narrative fit our observations beautifully for a long time. Hubble found small blue galaxies in the early universe as predicted. The cosmic microwave background showed tiny density fluctuations that would gradually grow into the galaxies we see today. Computer simulations confirmed that this bottom-up assembly matched our theories. Everything about the story seemed to make perfect sense. Then the James Webb Space Telescope began its observations. The 300 candidates that it found appeared far too bright. They were far too massive for their very young age. The Sleeping Beauty galaxies showed stellar populations that had formed and shut down. They had done this impossibly early in cosmic history. The 3 red monsters contained stellar masses that should not exist. They should not exist for many billions of years to come. The entire carefully constructed narrative began to unravel. The new picture that is emerging from Webb's data is more violent. It is more chaotic than we had ever imagined before. The early universe was not cautious in its construction. It was incredibly aggressive in its building of structure. Galaxies formed much faster, grew much larger, and evolved quicker. They did so much quicker than anyone had ever predicted. The star formation rates in these galaxies exceeded modern extremes. They exceeded them by factors of 5 or even 10. Gas was collapsing efficiently despite the processes that should have prevented it. This revised history has some profound implications for us. If massive galaxies formed so early in the universe, they would have ionized the universe much faster. This would change the entire timeline of the reionization epoch. Their stars would have produced heavy elements much sooner. This would have enriched the early intergalactic medium. Supermassive black holes could have grown much earlier and larger. This could explain some of the extremely massive black holes found at high redshifts. The formation of large galaxies early in cosmic history also affects our understanding. It affects how we understand galaxy evolution as a whole. If some galaxies reached massive sizes very quickly, their subsequent evolution would have been different from galaxies that grew gradually. They might have exhausted all of their gas supplies much sooner. This would have caused them to become dormant much earlier. Or they might have triggered different feedback processes that would have affected their later star formation. Cosmologists are also reconsidering what the cosmic microwave background tells us. The tiny fluctuations that we observe in that ancient light, they led to the predictions about the structure formation rates. If those predictions are now wrong, maybe we are misinterpreting the fluctuations. Perhaps the early universe had some additional physics at work. Physics that our current models do not yet include. The rewritten first chapter also changes how we think about our own galaxy. The Milky Way is known to have formed gradually over billions of years. But now we know that that was not the only path available. Some galaxies were able to assemble themselves very rapidly in the early universe. They then spent billions of years slowly evolving after that. The diversity of the formation mechanisms is much greater than we realized. This is not just about fixing the numbers in our theoretical models. It is about fundamentally reconceiving what happened during the universe's infancy. The first billion years were apparently much more dynamic, more efficient at building structure, and more capable of producing mature galaxies. More capable than we had ever imagined them to be. The revised chapter of cosmic history reads very differently from the old one. Instead of being slow and steady, it is now fast and furious, and we are still not sure that we understand the plot. Right now, the 300 candidates exist in a kind of scientific limbo. They are tantalizing, puzzling, and potentially revolutionary, but they are not yet confirmed as genuine early galaxies. The next phase of the research will be to determine which of them are real, which candidates are genuinely ancient massive galaxies, and which of them are just imposters that are fooling us. That determination will require the use of spectroscopy, and astronomers are already planning these crucial observations. Spectroscopy does not just take pictures of objects, it dissects their light into its component wavelengths. It reveals absorption and emission lines from the atoms and molecules. Each element is known to produce these lines at specific wavelengths. Hydrogen creates a series of lines that is called the Balmer series. Oxygen produces distinctive lines in the visible and infrared spectrum. Heavy elements like iron have very complex patterns of lines. When light travels across cosmic distances, all of these lines shift. They all shift together by the very same factor. By identifying the lines and measuring their shifted wavelengths, astronomers can determine the exact redshift of the object. This measurement is far more precise than photometric estimates that come from broadband imaging of the objects. Spectroscopy can pin down the redshift to within a fraction of a percent. For the 300 candidates, spectroscopy will answer the most basic question: how far away are they really from us? If most of them turn out to have lower redshifts than estimated, they will not be as early or as massive as they appear. They will become interesting objects, but not paradigm-breaking ones. If many of them are confirmed at high redshifts, above 7, the crisis for the field of cosmology will intensify. Spectroscopy also reveals what is producing the light from these objects. Stars have characteristic spectra that are dominated by absorption lines. These lines are from the elements in their atmospheres. Active galactic nuclei show strong emission lines from hot gas that is located near their supermassive black holes. Quasars have very different spectral signatures from normal galaxies. By examining the spectrum, astronomers can definitively determine the object type. They can determine whether an object is a galaxy, a quasar, or something else. The chemical composition of an object also comes from spectroscopy. The relative strengths of the different spectral lines indicate the elements. They tell us which elements are present and in what quantities. Early galaxies should show a very low metallicity. This means that they should have very few heavy elements. They would have formed from nearly pure hydrogen and helium. If a supposed early galaxy shows a high metallicity, it is probably not as ancient as it appears to be. Stellar population age estimates also improve dramatically with spectroscopy. Absorption features from certain elements only appear in stars of specific ages. Young stars show very strong hydrogen lines in their spectra. Old stars are known to show molecular absorption bands. By analyzing the full spectrum of a galaxy, astronomers can determine the mix of stellar ages within it. They can also estimate when most of the stars in it formed. Webb is already conducting spectroscopic follow-up on selected targets. The brightest of the candidates are getting the priority. This is because they require less observation time to study. Each spectrum takes between 2 and 10 hours of telescope time. This depends on the brightness of the object being observed. With hundreds of candidates to follow up on this is a huge project. Completing spectroscopy on all of them would take many years. The first results from these follow-up observations are starting to appear. Some of the candidates have been confirmed at high redshift. Others have turned out to be at much lower redshifts. This has ruled them out as being impossible early galaxies. A few have shown spectral features that suggest they are quasars, or they are other exotic objects rather than normal galaxies. The picture is slowly becoming clearer, but it remains incomplete. Future spectroscopic surveys will observe larger samples more efficiently. Webb will continue its follow-up observations for many years to come. Ground-based telescopes like the Extremely Large Telescope will also help. This telescope is currently under construction in Chile. Together, these facilities will eventually confirm or reject the candidates. The confirmed high redshift massive galaxies will become prime targets. They will be targeted for even more detailed observations. Astronomers will want to study their spatial structure and dynamics. They will want to search for supermassive black holes at their centers, and they will want to understand their star formation histories. Each confirmed object will become a laboratory for testing theories about the formation of the very first galaxies. Spectroscopy will also be used to search for any surprises. Some of the candidates might have unexpected properties that our current models do not predict at all. Unusual chemical compositions could hint at exotic formation mechanisms. Strange kinematic signatures might reveal unseen companions or merger events. The detailed information from spectra often raises as many questions as it answers. Within 5 years, we will have spectroscopic confirmation for most of the candidates. That data will determine whether the 300 galaxies represent a genuine crisis, or if they are just a temporary anomaly that can be explained. The telescope time has been allocated and the observations are being scheduled. Soon we will finally know the truth about these mysterious objects. When observations clash with our established theories, scientists are faced with a fundamental and difficult choice. Either the observations that have been made are somehow wrong, or the theory that we have been using needs to be revised. For the 300 early galaxies, we are fairly confident in the observations. The James Webb Space Telescope is working exactly as it was designed to. The photons that it has detected genuinely came from distant objects. This leaves the uncomfortable possibility that our theories need major changes. Perhaps they even need some form of new physics. New physics is a phrase that scientists use very carefully. It does not mean that we have to throw out everything that we know. Einstein's relativity did not invalidate Newton's laws of motion. It simply extended them to new and different regimes. Quantum mechanics did not erase classical physics. It just added new rules for how things work at atomic scales. New physics typically means discovering that our current understanding is incomplete. It does not mean that it is entirely wrong. Several areas of physics might need some revision to explain these galaxies. The most obvious one is our theory of star formation. Current models predict specific rates at which gas can collapse. These rates depend on gas properties, gravity, and turbulence. They also depend on magnetic fields and feedback processes. Maybe some important factor is missing from our current models. Perhaps star formation worked very differently when the universe was young. The gas back then had very different properties. If the star formation efficiency was dramatically higher in the early universe, our existing physics might be able to explain it without needing new laws. We would just need to understand why the conditions were so different. That is not new physics, it is just refining our existing physics. Dark matter presents another possible avenue for new physics. We know that dark matter exists through its gravitational effects, but we do not know what it is actually made of. Current models assume that it is entirely cold, dark matter. This means the particles move slowly and clump together efficiently. Maybe dark matter has some properties that we have not yet discovered. Perhaps it can interact weakly with itself in certain ways that would accelerate the formation of structure, that would constitute genuinely new physics for us. Some theorists are exploring modifications to gravity itself. What if general relativity is not the complete story? Maybe gravity works slightly differently on very large scales, or perhaps it worked differently at very early times. Modifications to gravity could change how quickly structures form. It could do so without invoking the presence of dark matter at all. Such modifications would represent a major new form of physics. Another possibility involves the nature of dark energy. We know that dark energy is driving the accelerating expansion of the universe today. But was dark energy weaker or stronger in the distant past? If dark energy has evolved over cosmic time in unexpected ways, it could have affected the rates of structure formation. That would require new physics beyond the cosmological constant. Even more speculative ideas involve modifications to quantum mechanics, or modifications to the theory of cosmic inflation. Perhaps the quantum fluctuations during inflation were larger than we thought, larger in some rare regions of the early universe. Those larger initial seeds would have grown into massive structures faster. Modifying the theory of inflation at this level would be new physics. Here is the critical question that we must now face. How much can we adjust our existing theories before we have to admit that we need some genuinely new physics to explain what we see? If tweaking a few parameters or refining our models of star formation solves the problem, that is not a revolutionary change in our understanding. It is just the normal process of scientific progress. Theories always need to be refined as new data arrives. But if no amount of parameter tweaking can make our existing models match, then we would face a real crisis in the field of cosmology. That is when scientists would seriously consider the need for new physics. We are not at that point just yet with these early galaxies. Many avenues still remain to be explored within our existing frameworks, but we are much closer to that threshold than at any time in recent decades. The history of astronomy includes several cases of this, new observations that forced genuinely new physics upon us. The discovery of the planet Neptune solved anomalies in Uranus's orbit. It did so without needing any new physics to explain it. But the anomalies in the orbit of Mercury eventually required Einstein's relativity. That was a completely new form of physics for its time. Dark matter and dark energy themselves represent new physics. They were added to explain observations that could not be fit with known matter. Perhaps the early galaxies will ultimately fit within ΛCDM. They might fit with just a few minor adjustments to the model, or maybe they are pointing to some serious gaps in our understanding. Gaps that will require new particles, fields, or fundamental laws to be filled. The implications of this depend on what future observations reveal. If spectroscopy confirms that many of the candidates are genuinely at high redshift, and they are genuinely massive for that early epoch, the pressure for some form of new physics will increase substantially. If most of them turn out to be at lower redshifts or are less massive, our existing physics will probably survive this challenge. Science works by pushing theories until they finally break. Then we build better and more complete theories in their place. The 300 galaxies are definitely pushing our current theories. Whether they will ultimately break our theories remains to be seen. James Webb's discovery of these 300 mysterious galaxies raises a question. If we have missed these objects completely until now, what else are we not seeing out there in the vast universe? Space is incredibly vast, and our observations cover only tiny fractions of the sky. The universe might be filled with other impossible objects. Objects that we have not yet found because we were not looking in the right way. Consider how the James Webb Telescope found these galaxies. It required an infrared sensitivity that previous telescopes lacked. Hubble looked at some of the very same regions and saw nothing. The objects were there all along, broadcasting their presence, but they were invisible to instruments that could not detect their stretched light. How many other types of objects are currently invisible to us? Invisible because we are using the wrong kinds of tools to look for them. Extremely distant quasars might be lurking beyond our current detection limits. We have found quasars out to a redshift of 7 and beyond, but these are only the brightest ones that are easy to see. Fainter quasars at even higher redshifts could exist in large numbers. They might reveal that supermassive black holes formed even earlier than we thought. This would add to the timeline problems that we are already facing. Primordial galaxies that are even older than the current record holders might be waiting. Webb can see back to potentially 150 million years after the Big Bang. It can do this under the most ideal of conditions. What if galaxies began to form even earlier than that, at 50 or 100 million years after the Big Bang? Such objects would be incredibly faint and difficult to detect. They would require extremely long exposures to even see. But it is possible that they exist out there. Dark galaxies represent another intriguing possibility. These are hypothetical objects that would contain large amounts of dark matter and gas, but they would contain very few stars, making them hard to see. With minimal star formation, they would produce almost no light. Our current telescopes detect galaxies by their bright starlight. Dark galaxies would be effectively invisible to these telescopes. We would need to detect them through their gravitational effects, or by observing the gas within them directly with radio telescopes. Failed galaxies might also exist in great abundance. These would be systems where dark matter halos formed as expected, but star formation never got started efficiently within them. They would contain some gas, but they would remain mostly dark. Finding them would require innovative new techniques to be developed. Techniques like radio observations of neutral hydrogen or gravitational lensing surveys. Then there are the exotic, theoretical objects that have not been confirmed. Black hole stars, if they ever existed, might be more common than we realize. Neutron star clusters could have formed in the early universe under special conditions. Strange quark matter might exist in forms that we have not yet recognized. Intermediate mass black holes also remain a deep mystery. We know that stellar mass black holes exist formed from collapsing stars. We have also found supermassive black holes in the centers of galaxies. But intermediate mass black holes weighing 100 to 10,000 solar masses, these objects are very rarely observed in the universe. The early universe might have produced them in significant numbers. They could be abundant but hard to detect without active accretion. Population 3 stars are the very first stars to have ever existed. They were made entirely of hydrogen and helium from the Big Bang. They have never been directly observed by astronomers. Theory predicts that they existed and should have been extremely massive. But maybe some of them survived for longer than we expected. Or perhaps they formed later in cosmic history than we think. Finding an actual population 3 star would be a revolutionary discovery. Primordial gravitational waves from the earliest moments might be detectable. They might be detectable with future instruments that are now being built. These waves could carry information about physics at incredible energy scales, scales that we cannot reach in any Earth-based experiment. They might reveal processes that fundamentally shaped how the universe evolved. Exotic dark matter candidates could produce observable signatures that we have not yet recognized in our data. If dark matter occasionally interacts with itself or with ordinary matter, those interactions might create signals in our telescope data, signals that we have been misinterpreting or dismissing as noise. Even weirder possibilities than these exist in our theories. Some theories predict the existence of cosmic strings. These are topological defects in spacetime left over from the early universe. They would be incredibly thin but enormously massive objects. Finding one of them would confirm aspects of theory that remain highly speculative. Pockets of a false vacuum might also exist out there. These are regions where space itself remains in a higher energy state than our surrounding universe. These would be incredibly dangerous if they ever expanded. They would convert the surrounding space to the true vacuum state, but if they are small and stable, they could persist undetected. The point is not that all of these exotic objects definitely exist. Most of them probably do not exist in reality. The point is that the universe is vastly larger and potentially far stranger than the small portion of it that we have observed. Every time that we build a more capable telescope, or we develop a new observational technique, we end up finding unexpected and surprising new things. The 300 impossible galaxies have taught us an important lesson. The early universe was more active and more capable than we had imagined. What will we learn next from our future observations? What other long-held assumptions will be challenged by future discoveries? Webb will continue to observe the universe for many years to come, potentially for decades if the mission proceeds successfully. Each year will bring deeper surveys that cover more of the sky. Other telescopes that are in the planning stages will add new capabilities. The flow of new discoveries is not going to stop. Somewhere out there, probably in multiple different locations, objects exist that would completely astonish us if we could see them. They are just waiting for the right telescope and the right wavelength. They are waiting for the right observational strategy to be found. Some of them might challenge our understanding even more radically than the 300 galaxies do. The universe has shown us repeatedly that it is more creative. It is more creative than our own imaginations. It is more diverse than all of our current theories. It is more surprising than our own expectations. The impossible galaxies are just the latest reminder of this fact, a reminder that we are still learning the universe's deepest secrets. What we discover next might be even stranger than this.